Okay, we're going to construct the graph of f of x equals 1 over x. First thing we're going to do is check for symmetry. Well, f of negative x is 1 divided by negative x, which is negative 1 over x, and that's negative f of negative x. So that by replacing x by negative x, we get the negative of what we get for x, which means that if we have a point on this side of the axis, if we reverse the coordinate x, make it negative, we're going to get a point that's as far from the x-axis but below it, because of course the value of the function is negative if this value is positive. So hopefully you understand that. But the point is now that this is symmetric with respect to the origin. This point reflects over to this point, and a line through the origin from here to here will be bisected by the origin. So knowing that that's going to be the case, we still don't know at this point that this is what the graph is going to look like, but we can make a brief table. Again, we're trying to wean ourselves from making extensive tables. But here we have x values. I'm going to use 0, 1/2, 1, and 2. Always a good set of values to start with if you have a basic function. Now, if that function has been translated 50 units in the x direction, those numbers aren't going to do you any good. But if you're calculating, if you're doing a basic function, this is not a bad place to start. And just with the positive values, we get y equals 1 over x has values. Well, 1 over 0 is undefined. Why is it undefined? Well, you can't divide by 0. You've been taught that as if it's a rule handed down on a stone tablet, but it just doesn't make any sense to divide by 0. If we, let's say, divide 10 by 2, well, we get 5. Now, you can think of grouping your numbers in 2s. How many groups of 2 does it take to make 10? Well, it takes 5 groups of 2 to make 10. Or you could think of counting to 10 by 2s, and that's the paradigm I want to use here. You go 2, 4, 6, 8, 10, goes in 10 times. Okay? How many times does 1/2 go into 10? Well, 1/2, 1. 1.5, 2, 2.5, 3, etc. It takes us 20 steps of 1/2 to get to 10. So 10 divided by 1/2 would be 20. Okay? What if it was steps of 1/10? Well, it would take 10 steps to get to 1, and 10 of those to get to 10, so it would be 10 times 10, or 100 steps. 10 divided by 1/10 is therefore 100. Okay, that's the reason 10 divided by 1/10 is 100. Now, the calculation you do with fractions is just a way of representing that fact. That's not the reason 10 divided by 1/10 is 100. That's a way of calculating 10 divided by 1/10. Okay, well, so if I want to count to 10 by tenths, I'll count 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, 7/10, 8/10, 9/10, 1. Then I got to do the same thing to get up to 2. I got to have 10. I got to count 10 times to get to 2. Well, what if I wanted to count to 10 by 1/1000th to indicate dividing 10 by 1/1000th? How many times does 1/1000th go into 10? Well, you need 1,000 of them to get to 1, and then 1,000 more to get to 2, and so forth. You need 10 times. You need 10,000. So 1/1000th goes into 10,000 times. Because, again, 1/1000th, 2/1000ths, 3/1000ths, 4/1000ths, 5/1000ths. To get to 10, I'm going to need 10,000 fingers. Okay, now let's think of what dividing 1 by 0 would be. That means we're going to count to 1 by zeros. Okay, well, let's start. 0, 0, 0, 0, 0, 0, 0, 0. We're not getting anywhere, and we're never going to get anywhere. So it makes no sense to divide 1 by 0. That's why it's undefined, not because of a rule that's handed down on a stone tablet. There are other ways to argue that it has to be undefined, but that one, I think, might be the clearest. Okay, so now we divide 1 by 1/2. Well, 1/2, 1. We count to 1 by 1/2, so we get 2. And then we divide 1 by 1, then we get 1. Now, we divide 1 by 2. Now, it doesn't make any sense to count by 1 by 1/2. We could count to, it doesn't make any sense to count to 1 by 2s because 2 is already bigger than 1, but we can count to 2 by 1s. 1, 2 takes 2 of them, and then take the reciprocal of that, we get 1/2. Okay, now I'm not being real rigorous about that argument, but we understand, I think, what's going on here. So we get, for x equals 1/2, we get 2, so we get the point 1/2, 2. For x equals 1, dividing 1 by 1 gives us 1, so we get the point 1, 1. If x is 2, we get 1 over 2, which is 1/2, so we get the point 2, 1/2. Now, as these numbers get bigger, we're going to get smaller and smaller fractions. If we go 3, 4, 5, 6, we're going to get 1/3, 1/4, 1/5, 1/6. Out here at 4 in particular, we're going to be half as high as we were at 2, because 1/4 is half of 1/2. Now, as we go toward 0, what's going to happen? Well, we could, there are a lot of ways to go towards 0, but let's just go, we got 1/2, we could go 1/3, 1/4, 1/5, 1/6, 1/7, and so forth. Now, clearly we eventually get out to 1/1000th or 1/1,000,000th or 1/1,000,000,000th, and we're still to the right of 0, because any positive number is going to appear to the right of 0. Now we're going to have trouble making a mark 1/1,000,000,000th of a unit to the right of the origin, so we're not practically going to be able to do that, but we know that when we divide 1 by 1/1000,000th, we're going to have to count to 1 by 1/1000,000th. It's going to take us 1,000,000,000 steps. So we're eventually going to have a point 1/1,000,000th, 1/1,000,000,000. Now 1/1,000,000,000 is going to be like 100 million feet, which is 200,000 miles high, okay, if I did that calculation correctly. But we're still going to be to the right of the y-axis, not by any distance we can perceive on this graph, but we're still going to be to the right of the y-axis, and we're going to be really, really high. But of course, 1,000,000,000 isn't the end of the numbers. Okay, 1/1,000,000,000th isn't the smallest number that you can have here. There's no limit to how small the x values can get, so there's no limit to how big the y values can get, and you're still to the right of the y-axis. So we have this vertical asymptote. Eventually, it gets so vertical we can't tell that it's not perfectly vertical, although, in fact, it isn't. As we go to the right, there's no limit to how big these numbers can get, so there's no limit to how small 1 over that number can get. We can go out to 1,000,000,000 here, and how far are we going to be above the x-axis? We're going to be 1/1,000,000,000th of a unit. Again, so close we can't see it on this graph, but theoretically, if we have an infinitely thin line, there's going to be a separation between the x-axis and a point 1/1,000,000,000th of a unit above the x-axis. Of course, it's going to be 1,000,000,000 units out there. Again, you know, a couple hundred million, a couple 100,000 miles. Going to be way out there. Okay. Still above the x-axis, so we have this asymptote with the x-axis. So in constructing this graph, we want to be sure we understand we have asymptotes. That's going to be very, very important when we get to analyzing rational functions. Now, I make the statement here a little more concise. As x goes to 0, there's no limit to how small x can be, so there's no limit to how many times x can go into 1. So as x goes to 0, we get an asymptote with the y-axis. And for large x, 1 over x stays positive but approaches 0. There's another asymptote out here. So there's our graph of y equals 1 over x. I need to add the symmetry argument. We have 1/2, 2. If we reflect that through the origin, it means we make a line from this point through the origin and continue it on until we're at least this far on the other side. And when we are this far on the other side of 0, we have our point. And clearly then, if this point is 1/2, 2, this point is -1/2, -2, by the symmetry and by the geometric fact of the reflection. And 2, 1/2, of course, then reflects through the origin to -2, -1/2, 1, 1 to -1, -1. So that we have this shape reflected through the origin, giving us this shape. And of course the asymptotes are going to reflect, and you can do that point by point and see how it works out.